Chapter 13, Oceans and Coastlines. In this chapter, we will cover our changing oceans, the ocean floor, ocean waters, the ocean circulation, tides, wave action and coastal processes, shoreline features, and shoreline protection. About 71% of the Earth is covered with seawater. The oceans were mostly in place by about 4 billion years ago. They are the final frontier for research on Earth. Natural processes and human activities impact our oceans and coastlines. In some cases, these changes can make places disappear beneath water and force people to relocate away from everything they have ever known. About 71% of Earth is covered with seawater. The oceans were mostly in place by about 4 billion years ago. They are the final frontier for research on Earth. Oceans are dynamic. Water is continually in motion. The ocean and atmospheric circulation patterns move the heat around and strongly influence climate. Coastlines are also dynamic, advancing and retreating depending on the balance of erosion and deposition. Here's the rugged coastline near Malibu in California. As you can see, this has been developed. Malibu was recently on fire and a lot of these homes burned. The rock layers in the cliff here provide a greater resistance to the coastal erosion that the sand dunes present along the Atlantic coast. How do oceans and coastlines change? Coastlines can advance or retreat. In the short term, the position of the coastline can change depending on daily tides and seasonal variations in stream flow. Climate cycles measured over decades, centuries, or millennia can show rises and falls in sea level. Tectonic cycles occurring over thousands to millions of years can revitalize coastlines through uplift. Humans can influence oceans and coastlines as well, and be strongly affected by oceans and their weather, for example, hurricanes. More than a quarter of the U.S. population lives along the Atlantic and Gulf coasts. From what you learned about plate tectonics, would you expect the depths to be the same throughout the world's oceans? The depth of the ocean, surface to floor, varies from 0 meters along the coast to a maximum of nearly 7 miles along the Mariana Trench. Mount Everest would sit in the trench with over 2,000 meters to spare. More than 1,500 people have stood atop Everest, and only 2 have visited the deepest region of the ocean floor. The average land elevation is less than 1 meter, but average ocean depth is 2.3 miles. The volume of water in the oceans is nearly 10 times the volume of dry land that lies above sea level. If erosion leveled the continents, all the eroded material would fit in the ocean basins with room to spare. The elevation of the ocean surface varies because the elevation of the ocean floor varies. Bathymetry, the measurement of depth to the ocean floor, and the mapping of its features. Data from ships and submarines are combined with satellite data to reveal the topography of the ocean floor. The ocean floor has mountains, valleys, plains similar to those on land. Masses of rock on the sea floor exert gravitational pull on the water, causing it to pile up and form a mound on the ocean surface. Sea level is assumed to be 0 meters. Sea level changes are due to changes in the shape of the ocean basins or long-term climate changes that trap water in ice caps or cause ice caps to melt. The sea surface has bumps and low points. A satellite measures the difference in height between the bump over a volcano and the surrounding ocean. Radars on satellites are used to measure variations in gravity, which reveals the ocean floor topography. There are 4 major depth zones: the continental shelf, the abysmal plain, the oceanic ridge, and the ocean trenches. The passive margin zones are the continental shelf, the continental slope, the continental rise, and the abysmal plain. The active margin zones are the continental shelf and slope, the trench, and the abysmal plain. Zone 1 of the continental shelf is the shallow ocean floor adjacent to the continent, the submerged continental crust that slopes away from the coast. The maximum depth is a few hundred meters. When adjacent to passive margins, it's wide. It's narrow when adjacent to active margins. The width of the shelf decreases as the sea level falls and increases as the sea level rises. During the last Northern Hemisphere glaciation, when sea level dropped, the continental shelf off the coast of New Jersey was exposed. The Hudson River cut a deep, narrow canyon into the exposed shelf on its way to the lower sea level. The canyon was later submerged when the sea level rose. The Monterey Submarine Canyon was cut into the shelf by a river flowing during the interval of lower sea level associated with the last time much of North America was covered with ice. Zone 2, the abysmal plain. The continental slope and rise are the transition to the abysmal plain. Rapid deepening of the ocean leads to a gentler slope that ends at the abysmal plain. The continental slope is marked by a rapid deepening of the ocean, a couple thousand meters. Continental rise is where sediments swept off the slope accumulate. The abysmal plain is the deep ocean floor. It's over 4 kilometers deep and are some of the flattest portions of Earth's surface. It's covered by layers of very fine sediment and may be dotted by seamounts, which are underwater volcanoes. Zone 3, the oceanic ridge. The oceanic ridge system is a submarine mountain chain that can be traced around the world. Ocean floor rises from the abysmal plain to the ridge. 90% of Earth's volcanic activity happens at ocean ridges. These don't heat the water very much because heat rapidly dissipates. The depth is about 3 kilometers above the ridge crest. The central valley beyond the ridge crest is the region of submarine hot springs, hot smokers. They are home to some really strange life. Here's a hot smoker vent where the mineral-rich heated waters are expelled into the cold waters of the deep Pacific Ocean. And right here you can see the equipment that's being used. Here's a white crab and a tube worm colony. Zone 4, the oceanic trench. Active continental margins where 2 plates converge form an oceanic trench near the subduction zone. Narrow and deep, in fact the deepest places on Earth. This marks the place where oceanic lithosphere descends into the mantle. It's 4 to 7 miles deep. Where did our oceans come from? Early Earth was a hostile, hot mass of nearly molten rock. Violent volcanic eruptions put gases, including water vapor, into the air. As Earth cooled, this water vapor condensed into liquid water. The more the planet cooled, the more water could collect in the hollows and baby oceans that grew into our present oceans. Although the water in the oceans has been present for about 4 billion years, the present ocean basin configuration is the result of plate tectonics, and no ocean basin is older than about 200 million years old. Even now, oceans and seas continue to grow or shrink as plates diverge or converge. Oceans are salty because seawater contains dissolved salts and minerals. Most of the dissolved solids in seawater is common salt, sodium. Salinity is the measure of the concentration of salt in seawater. The more salt there is, the higher the density. What variables might influence what parts of the ocean are saltier than others? Here's a table showing the major elements and compounds that are found in seawater. As you can see, there's chloride and sodium and sulfate, calcium, magnesium, potassium, and trace elements here. I see iron. Here's the ocean temperatures and latitude. The average annual mean temperature of the world's ocean surface varies with the latitude. The numbers represent the temperatures in degrees Celsius. Of course, the temperature of the ocean would vary with the latitude. Here would be close to the equator, and as you go toward the poles, it would be cooler. They have less direct sun toward the poles than at the equator. Salinity is influenced by temperature, mixing caused by currents, freshwater input from rain, streams, and melting ice, the size and shape of the basin. Salinity is highest where temperature is high and the precipitation is low, because evaporation leaves behind the salt. If you have salt water, the only thing that can evaporate from that water is the H2O. It has to leave the salt. The salinity of the ocean also varies with depth. Salinity changes rapidly at a depth of about 500 meters. Rapid change in salinity at depth is the halocline. Salinity values are fairly uniform below this depth, consistent values of about 34 parts per thousand. Why? Because deeper waters are not affected by surface processes that change the salinity. For example, evaporation and stream flow. Water cannot evaporate anywhere except the surface. It's the only place that the water can change from a liquid to a gas. Temperatures vary according to latitude. The ocean temperatures are affected by solar insolation, ocean currents. Temperatures are the highest where solar energy is the highest. Water has a high specific heat. The amount of thermal energy required to raise the temperature of 1 gram of material by 1 degree Celsius. The temperature of a material with a high specific heat will not rise as rapidly as one with a low specific heat. Water can absorb a lot of thermal energy without displaying much of a change in temperature. Water actually is way slower at absorbing and releasing heat than land. Why is it important that water has a high heat capacity? Well, water can absorb, store, move, and release a lot of heat energy. This is of major importance to global climate patterns. The density of water decreases with the increase of temperature. Of course it does. The density of water means how many molecules are in a specific space. As water gets warmer, it needs more space. It vibrates more, therefore it takes up more volume. Warm water is less dense than cold water. Below 4 degrees Celsius, this changes. The density of really cold water decreases, especially when it goes from liquid to solid form. There are shallow layers of ocean water, relatively warm, which are warmed by solar radiation. The relative uniform temperatures as water is mixed by currents. Water density differences. Icebergs float on a bay on Greenland because the ice is less dense than water. Ocean temperature versus depth and latitude. The north-south profile through the Pacific Ocean along the 150-degree west meridian. This illustrates the range of temperature with depth and latitude. The temperature decreases with the depth. These temperatures are corrected for the temperature changes caused by increasing pressure with depth, thus called potential temperature. The most rapid temperature changes, the thermocline, occur between 100 and 500 meters, which is about 328 and 1,640 feet. The black pattern represents the seafloor bathymetry along this profile. Temperatures are expressed in degrees Celsius. The third factor that affects density is pressure. The uniform increase in pressure with depth slightly increases the density of the underlying water. Salinity, temperature, and pressure combine to create a density profile. The pycnocline is rapid increase in density from 200 to 1,000 meters depth. Density is uniform below the pycnocline. Ocean water. There are 3 main vertical density layers. There's the surface, which is about the top 2%, the middle, which is 18% of the ocean, and the bottom is 80% of the rest of the water. Here's a graph showing the density versus depth. The density is the lowest at the surface, right here. So it would be toward this side of the graph. It increases to a depth of approximately 1,000 meters, and then the density is generally uniform below the pycnocline. This is the distribution of ocean currents. Notice the circular patterns, also called gyres, which are clockwise north of the equator and counterclockwise south of the equator. Which current transports the warm water and which carry the cold water? Well, right through over here, you would see the Gulf Stream, which influences the coastal weather of the United States, as well as Ireland, Scotland, and England over here. The winds move the ocean water. There's friction between the wind and the surface water. Oceans follow prevailing wind direction, except where current encounter a barrier, like a landmass. Only 10% of the world's ocean water is moving in surface currents. This is a narrow, high-temperature Gulf Stream. Here's how the Gulf Stream travels along the coastline, and then it goes over toward Ireland, Scotland, England. The circular patterns in the atmosphere generate gyres. It's clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. Water takes months to years to complete one gyre circuit. The fast-flowing boundary currents at the western extents of the gyres redistribute warm tropical water toward the poles. For instance, the Gulf Stream. Eastern portions of the gyres carry colder water from the high latitudes toward the equator. For example, Canary. Ocean circulation, currents. The Atlantic Ocean currents and sea surface temperatures averaged for April through June. The Gulf Stream and the Brazil currents represent bands of warm currents. These are yellow and light green colors. They are along the Atlantic coastline of North and South America. The Canary and the Benguela currents are broader regions of cooler water, which are the dark green, that move south and north along the coasts of northern and southern Africa, respectively. There's something called the Coriolis effect. The Coriolis effect is in the atmosphere as well as the ocean circulation pattern, so it affects the global winds and the ocean currents. It deflects to the right in the northern hemisphere and to the left in the southern hemisphere because the Earth rotates from the west to the east. That's the direction that it spins. The objects near the equator actually move faster than those near the poles because there's more distance to cover in the day's rotation. The planet beneath the circulating wind and water moves its position, leading to the deflection. You can compare this to a merry-go-round. Imagine that you are standing at the edge of a merry-go-round and you are going to throw a ball to your friend watching you on the merry-go-round. The merry-go-round is spinning. Can you throw the ball straight to the person? Or do you have to aim it a little bit behind or in front the person so that it goes directly to them? It can't go straight. You have to curve it because you're spinning and the ball is not going to go where you think it's going to go if it goes straight. Imagine you're in Panama City, Florida. At noon, you fire a rocket directly toward Columbus, Ohio. Pretend like this is a merry-go-round. The rocket has a northward velocity, but it also has a faster eastern velocity due to the Earth rotating east. The rocket will land east of the city of Columbus, the apparent deflection. So it's going to curve. It's going to go this direction. Continents can affect ocean circulation patterns. The closure of the Isthmus of Panama influenced circulation patterns in the Atlantic. The western currents forced north, and it strengthened the Gulf Stream. The warmer waters into the North Atlantic. It raised temperatures in Europe, and the winters were milder in Europe and North United States. This shows the distribution of continents and oceans between 14 and 50 billion years ago. The Isthmus of Panama was open, which allowed the water to circulate between the Atlantic and the Pacific Oceans. When the isthmus closed, the Atlantic Ocean currents shifted northward, and the proximity of the southern continents to Antarctica kept it ice-free, and it was warmed by the currents from the Pacific, Atlantic, and Indian Oceans. Plate tectonics resulted in the northward migration of Australia, Africa, and South America, and a circumpolar circulation pattern developed that surrounded Antarctica with cold ocean currents. Antarctica used to be mostly free of ice. About 34 million years ago, ice growth was triggered. There was a separation of South America and Australia from Antarctica. But before this occurred, warm tropical waters moved south and warmed Antarctica. The separation of Antarctica and South America opened up the strong currents in the Southern Ocean. Some of the strongest currents in the world are located between South America and Antarctica. This isolated Antarctica from moderating ocean currents. The Gulf Stream carries high salinity, warm waters from central Atlantic to the higher latitudes. The water cools as it travels north, and the cold, salty water sinks toward the bottom of the North Atlantic near Greenland and Iceland. The sinking water is then carried southward along the bottom of the Atlantic, and this is called the North Atlantic Deep Water. When it reaches Antarctica and it's diverted eastward to the Indian and Pacific, the deep current eventually comes up in North Indian and Pacific Oceans, this is called the upwelling. It brings nutrients to surface waters. The pattern of the deep currents is termed thermohaline circulation, which is driven by both salinity and temperature. This shows the global thermohaline circulation. The youngest part of the ocean floor is at the oceanic ridge. The high heat flow due to rising magma contributes to higher elevations along the oceanic ridge system. In the oceanic trench, the deepest section of the ocean floor marks a plate boundary where the oceanic lithosphere and the Nazca Plate descends a subduction zone adjacent to South America. The continental shelf. It's shallow. The submerged section of the continental crust present along both passive and active margins, but wider at passive margins. Some of the oldest and flattest sections of the ocean are located landward of the oceanic ridge. The thermohaline circulation is a global oceanic conveyor belt that transports water through the oceans as a result of density contrast related to differences in temperature and salinity. In a normal year, the Pacific Ocean waters are heated. The trade winds blow warm water toward the west. There's a cold upwelling that occurs off the coast of South America in an El Niño year. The western trade winds diminish. The warm water remains in the Pacific, causing heavy rains to occur in South America. The surface salinity decreases, reducing the upwelling, and droughts then occur in the western Pacific. In a La Niña year, the cold conditions dominate. There's droughts in South America and western United States. There will be severe weather in the western Pacific. Oceanic circulation. Sea surface temperature anomalies and elevation for El Niño and La Niña events. The red colors indicate the water temperatures. They were up to 9 degrees warmer than normal. The blue colors show water temperatures that were up to 9 degrees colder than normal. In the top, the El Niño featured warm waters in the red and the higher areas in the eastern Pacific Ocean. in the bottom. The La Nina event had cooler waters, which are blue, and lower sea surface elevations. How do the sea temperatures along the western United States coast vary between these events? The phases of the moon. One of the bits of evidence that the Earth orbits the sun, not the other way around, and that the Earth is round. The moon actually orbits Earth every 27.3 days. The new moon is when the moon is between the Earth and the sun. Therefore, all we see from Earth is the shadow. The full moon is when the Earth is between the sun and the moon, and therefore we see it's all lit up. The moon affects tides. The tides are changes in the sea surface height caused by the gravitational attraction of the moon and a little bit by the sun too. The water envelope is quite exaggerated. It's this egg-shaped section right here. The spring tides are shown in this drawing on the left. It's the largest gravitational pull that caused the largest tidal bulge and the highest tides. The sun and the moon actually work together. See, the sun and the moon are on the same side of the Earth here. Neap tides are shown in this drawing. That's when the gravitational pull is the smallest and result in the smallest tidal bulges or the lowest tides. The sun and the moon are on opposite sides of the Earth. A spring tide is when the sun and the moon exerting pull on the Earth in the same direction. It occurs during the new moon. The neap tides, the sun and the moon exert the pull on the Earth in different directions. What would happen to spring tides if the moon were farther away from Earth? Would the tides be higher, lower, or no change? Because the Earth rotates faster than the moon orbits, the location of the tidal bulge changes. The moon is not always over the same spot on Earth. The moon is essentially stationary while Earth rotates on its axis. Imagine tidal bulges as stationary as Earth rotates below them. A coastal site would rotate below two tidal bulges, or high tides, on opposite sides of the Earth each day. It would pass through two minima, or low tides. Equal but opposite tidal bulges on the side of Earth away from the moon, due to a balance of forces associated with gravitational attraction of the moon, rotation of Earth-Moon system about a common center of mass called a barycenter, and rotation of Earth on its axis. Depending on the position of the moon relative to Earth and the latitude of a coastal site, the two daily tides may be very similar, semidiurnal or varied, mixed. In panel B, back here, notice there's an equatorial coastal city that would have a semidiurnal tide pattern, while at mid-latitude the pattern would be mixed, very high on the right side of the image and low on the upper left side. The influence of the moon's position on the location of the tidal bulge on Earth. The two daily tides might be very similar depending on the position of the moon. An equatorial location would have a semidiurnal pattern where a location around the mid-latitudes would have one high, way larger than the other. These graphs represent the tidal patterns. This one being the semi-diurnal tide. The middle one is the mixed tide. And this one is the diurnal tides. You can see here's a new moon, half moon, full moon. And there's the full, half, new. In the open ocean, water simply bobs up and down. The wave shape, or the form, moves while the water particles follow a circular path and remain in place. Wave size, speed, and direction are controlled by winds. The waves we see in the ocean are the result of wind energy transferred to the surface water. Wave action affects only surface waters. It does nothing to anything underneath. The motion decreases downward to a depth equal to about half of the wavelength, called the wave base. The deeper the wave base, the more volume of water is involved in the wave. Wave heights. The red, orange, and then the yellow are the largest waves, shown in this drawing. Wind-generated waves increase in size with increased wind speed. The wind speed and distance over which the wind blows, called the fetch, determine the frictional force and ultimately the wave height. Large waves come from high velocity, steady winds blowing across a wide area with no obstructions. Which ocean do you think has consistently taller waves, the Atlantic or the Pacific? Why do you think that? Well, think about Hawaii. Hawaii is located right here. And look, there's yellow. The yellow area indicates some of the largest waves. Look at all this open ocean here. In Hawaii, some of the largest waves are there because of all the open ocean and the trade winds. As a wave approaches shore and shallower water, it is slowed down by friction and its length decreases, so the wave becomes taller and steeper. The wave eventually collapses due to over-steepening, called a breaker. The water actually moves forward here. The path of Hurricane Katrina is shown right in here. 42040 is a station that actually recorded wind speed and wave height. Here, the average wind speed for 10-minute intervals is recorded. And here, the significant wave height. You can see it kind of correlates with the wind speed right here. Rip currents. They're narrow currents of water flowing through gaps in sandbars lying just offshore. And you can see right here through this sandbar, there's a rip current. Rip currents are caused by variations in the surf zone, such as sandbars and channels. You see the location in the picture that might be dangerous if you were swimming? Yeah, you wouldn't want to be swimming out here. Do you think you could see it from the beach? If you know what you're looking for, you can, yes. Thousands are actually rescued from rip currents each year, and rip currents cause at least 100 deaths in the United States every year. And like I said, if you know what to look for when you're on the beach, you can avoid the rip current. Now, if you're swimming out there and you do accidentally get caught in a rip current, don't try to swim directly back to shore. Swim along the shore sideways to it, parallel to the shore, so that you can actually swim out of the rip current. Yes, you'll be headed out towards sea, but because the rip current will be pushing you out, but you will eventually come out of the current and then be able to swim back toward shore. Irregularities in the shoreline or changes in seafloor can change the shape and the direction of waves, can cause the bending of the waves toward the shore. That's called refraction. These waves are refracted toward the headlands. Refracted waves accelerate the headland erosion. So whatever's sticking out in the ocean right here is going to get eroded first. Eroded material is deposited in the sheltered nays, the areas between the headlands. Here, continued erosion straightens the coastline, so the part that was sticking out is no longer sticking out. It's been eroded away and deposited in between the two headlands and smoothed out. The rotating blades of current turbines look like underwater wind turbines, and they do produce power in pretty much the same way. Turning waves into energy. Ocean waves are actually energy moving through the oceans. If that energy could be harnessed, it would be clean and renewable. What's the best location to build an ocean wave-driven power generation facility? What problems might you face? Shorelines are constantly changing as the materials are eroded, transported, and deposited through a process known as the sediment budget. This headland is being eroded. This is White Bay Park in Northern Ireland, a rocky coastline that's dominated by cliffs and low-lying wave-cut platforms. This is Strathy, Scotland, a low-lying coastline that's dominated by long beaches and dunes. This is a photograph of Assateague Island in Maryland. This is a narrow, elongated barrier island that separates the ocean from the mainland. And here you can see this is the ocean, and this would be the water between the island and the mainland. What do waves do to the coastlines? Well, they cause erosion, wearing away headlands and filling in the bays. It straightens out the coastline. It transports material and deposits sand and other materials. In California, there were 12 homes along this stretch that were condemned when the cliff actually retreated 33 feet. And this is still going on in California and other places around the world. The erosion rates of the coastline along the Atlantic shore and the Gulf Coast are about 3.3 feet per year on average. The erosion is worst on loose, unconsolidated sediments, and it can be accelerated by surges caused by storms. Shorelines can also experience deposition. The shoreline grows in width with deposition of sediment. Head-on currents carry sediment onto and off the beach, but it may deposit sand in the sandbars offshore during storms. Longshore currents transport the sediment parallel to the beach in the surf zone. A spit is a sandbar that partially blocks a landform. Baymouth bar, sandbar that completely blocks a channel. And this one is just about blocking this channel right here. This is Puget Sound. It's almost cut off from the ocean by a narrow spit that could become a Baymouth bar. This is Tomales Bay near Point Reyes in California before a storm. And here it is after a storm. Same place. Sand was transported along the shoreline from the left side of the image toward the right side and deposited. A lot of it was deposited. The natural features that protect coastal residents of Florida from erosion are the tall sand dunes behind the beaches. It protects against large storms. There's wide, stable beaches that absorb wave energy. There's also exposed offshore sandbars to absorb the force of breaking waves. And there's one missing from this list, and those are the coral reefs that are located offshore. These features are not found at all beaches, and humans can erect artificial barriers to help slow erosion, but these features may speed up erosion in other coastal locations. The sediment budget. The sediment budget is the balance between the material deposited on the shore and the material eroded from the shore. Humans can influence the sediment budget and coastline features by their actions. For instance, if humans were to dam a major river, it can cause a result in sediment starvation because the sediment that would have been deposited along the shoreline is trapped upstream. Humans can also build structures to try to combat dangerous erosion processes. Such as a seawall. This seawall was built to try and slow erosion of a cliff north of Monterey, California. It was built of rock and placed at the base of the eroding cliff. But do you see how the erosion is even worse where the seawall ends? Look down here. Look at the sides where there's no seawall. A groin can be built, which is a wall-like structure built perpendicular to the shore, and there barriers to long-shore currents. It causes deposition on the upside, on the up-current side, but erosion on the down-current side. This groin was built across from the LA International Airport. Breakwaters can be built. These are barriers that are built offshore to protect part of the shoreline. It slows the waves and allows the beach to grow behind them. The unprotected parts of the shoreline often erodes more quickly when these are built. Here's a picture before Hurricane Ivan. I want you to take a good look at this building right here with the pool and the little dune here with the walkway that goes across. This is before the hurricane. And here's a picture of the same building after the hurricane. There's no sand dune, there's no walkway, the pool is filled in with sand, and the building has collapsed.